All right, next we're going to take a look at how we can find the area of regular polygons. Reminder that a polygon is a closed, two-dimensional geometric shape formed by straight line segments. It has at least 3 sides and 3 vertices or corners. A regular polygon is a polygon where all sides are of equal length and all of the interior angles are equal in measure. So we are only going to be talking about finding the area of regular polygons. So again, all side lengths are the same, all interior angle measures are the same. So here's a reminder of some regular polygons. Our triangle has 3 sides, any quadrilateral has 4 sides, pentagon 5, hexagon 6, heptagon 7, octagon 8, those are your stop signs. Nonagon 9 sides, decagon has 10 sides, and a dodecagon has 12 sides. All right, an inscribed polygon is a convex polygon whose vertices all touch a circle. So it's inscribed inside the circle, and the corners or the vertices touch the outside of the circle. A circumscribed polygon is a convex polygon whose sides all touch a circle. So now the circle is inside of our polygon. So we're going to find the area of each polygon with the given information. So a regular nonagon, so remember a nonagon means 9 sides, and we drew it here for you, inscribed in a circle with a radius of 5 feet. So here's our diagram. Remember, radius means the distance from the center to the outside. So if I would draw a segment from the center to any corner, or any vertice, I should say, of my nonagon, we know that that is going to be 5 units long. And so I can draw another one here. Didn't quite make it, there we go. And again, that's 5 units because the radius the whole way around the circle is 5 units. We also know that the distance the whole way around a circle is 360 degrees, like that angle measure the whole way around. And so if we would keep drawing these triangles, because it has 9 sides, we would end up with 9 different triangles. And so this 360 degrees is being evenly divided by 9, because this is, each of these triangles would be the same size because it's a regular polygon. So to find this angle measure, I'm going to take 360 degrees and divide it by 9, since there would be 9 triangles to fill up the whole thing. And so I see that it would be 40 degrees. And so now I can use my area of a triangle formula that we were working on the previous pages. If I take 1/2 times the 2 side lengths times the sine of that included angle, that will give me the area of the triangle. And then it would take 9 of these triangles. Like if I keep going and draw all of these triangles, there's going to be a total of 9 of them because there's 9 sides to a nonagon. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And all of these lines that I drew would be 5 units long because they're all radii of the circle, and each one of these angles would be 40 degrees, since it's evenly being split up because it's a regular polygon. So if I find the area of this one triangle here, I can just multiply it by 9 to find the area of the entire figure. So if we type this on our calculator, so 1/2 times 25 times the sine of 40 degrees, again, always make sure you're in degree mode on your calculator if we're entering it in a trig ratio in degrees. And then times 9, since 9 triangles would fill up the polygon, we'll see that the area of this nonagon would be 72.3 square feet. All right, so now we are looking for the area of a regular octagon with a side length of 7 inches. So an octagon, remember, has 8 sides. So if I quick draw myself, or, maybe I'll just copy the diagram here. And we make this bigger. All right. So from the distance in the middle out to the outside, I could form a triangle. And again, it would take 8 of these triangles to fill up my octagon. And what they're telling us is every side is 7. So this is 7, 7, 7, 7, 7. All right, so we've got to do a little more work because I only have one side. I don't have an included angle or anything, but I can still use my trick to figure out what this angle measure is here. So, you know, the whole way around this would be a circle. So if I can take 360 degrees, so again, to find this angle, I'm going to take the 360 degrees, that would be the whole way around, and divide it by 8, since there are now 8 triangles in this, because it's now an octagon. And so if we take 360 and divide it by 8, we're going to get 45 degrees for that. So I'm going to draw my triangle outside of my octagon now. So we know the base is 7, this is 45 degrees. And so I could think about finding the height of this so that I could find the area of the triangle with 1/2 base times height. So if we want to find the height of that, we know our right triangle trigonometry. You know, if the entire angle up there was 45 and I'm just splitting it in half in order to draw my little right triangle. Oops. So this is now 3.5. This angle would now be half of what it was, so it'll be 22.5 degrees. And we need to know what this value is here. That would be the height of the triangle, so I should call it h. H for height. I need to find that value there, and then I can do 1/2 base times height to find the area of that triangle. So we know this angle and this side, so I could do a tangent since I know opposite and I'm looking for adjacent. So tangent of 22.5 degrees, and that will equal opposite, which is 3.5, over adjacent, which I'm calling h. So we'd cross multiply and divide and see that h would equal 3.5 divided by the tangent of 22.5 degrees. So let's see what h is. So 3.5 divided by tangent, 22.5 degrees. And so we will get 8.4 approximately for the height of our triangle. And so then area of a triangle, you know, the basic formula we learned long ago, area equals 1/2 base times height. Well, they told us the base is 7. We just figured out that the height is approximately 8.4. And then I'm going to multiply that by 8 because, again, it takes 8 of these triangles to fill up my octagon. So if I type this all in a calculator, 0.5 times 7 times 8.4 times 8, we see that the area of our octagon is 235.2 square inches. And this isn't the only way we could go about this. We could have also figured out the bottom angle measures and used those as well. There's lots of options. So if we wanted to go about finding the side length, so that's one option for how we can do this. Let's take a look at another option just to show you all the possibilities. So the other thing we could do is use our new formula that says, this 1/2 the length of the two sides times the sine of the included angle.
Those students who need a picture retake or are not here on picture day from the following CLCs report to the auditorium at this time. DeMarzo, Mrs. Detweiler.
So if we think about the base being 7, and we want to find out what the outside length is here, we could do that as well and then use that new formula. So again, we would still need to think about our little right triangle and the fact that this is 22.5 degrees up here. We know that this is 3.5, and we could find this outside length. So we could do the sine, since we have the opposite and we're looking for the hypotenuse. So we could do the sine of 22.5 degrees, and that's going to equal 3.5 divided by x. So we could cross multiply and solve. So if we do 3.5 divided by sine of 22.5 degrees, we get approximately 9.1. And so then with that new area formula, we would do 1/2 times 9.1. So each of these outside values would be 9.1. So, and then the sine of the 45 degrees, that is this top angle. So 0.5 times 9.1 times 9.1 times sine of 45 degrees. And then we have to multiply that by 8 because there's 8 triangles in that octagon. So slightly different based upon rounding, but both would be acceptable as final answers here. All right, so lots of options for how to do it, but basically we can use these triangles that would fill up these regular polygons in order to find their area.